So stationary points are is another way of saying a turning point. It's basically where a graph is not going up or down. So this graph is going up, 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 and then it stops. Well, it doesn't stop, but it turns, and then it goes down, 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 then it turns, it goes up, 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 up. So this point here is a stationary point, not going up or down. This point here is a stationary point, not going up or down. And we know, sorry about the drilling, we know that at a stationary point, at a turning point, the drilling stopped. The gradient is going to equal 0 at these points. So this is really nothing particularly new from C1. So we're looking for points where the gradient's 0. Right. Okay. So let's differentiate.
Okay. So dy by dx is 6x squared. Bring down the power, and that cancels with the 2 on the bottom, so that's 7x minus 5.
Yep, and then we wanted to find stationary points, so that's turning points.
That's where the gradient is 0.
Gradient's 0.
6x squared plus 7x minus 5. Right, so we want two numbers that times to 30 and add to 7.
5 and 2? No, 5 and 2 isn't 30.
10 and 3?
Yeah.
10 and 3.
Yeah.
Right, so we need to do
6x squared
6x squared
plus 10x. Or, yeah, you can do it either way around.
minus 3x plus
Yeah.
10x minus 5. So that's that way, because I'm going to factorise that.
Yeah.
Let's get in there. Right, so that is 3x, and we've got x minus 1.
Yep.
And that one is, we pull out 5, so we've got
X minus 1.
no,
Yeah. No. That's because look,
Oh,
3x
2.
times, yes, there we go.
2x minus 1.
That's better.
Yeah, brilliant. Okay, so then our two factors are 3x plus 5 and 2x minus 1. Yeah,
We'll just shout over the drilling.
so x is minus 5 over 3 and x is a half.
Yep.
Brilliant.
Right, what were we doing?
Those are the coordinates. Well, that's the x
Okay,
coordinates.
so we've got a cubic, a positive cubic. So really sorry about this drilling, but they're going to do it all day, so we've got to carry on. So we've found that the x values corresponding to the two turning points are minus 5 over 3 and a half.
Yeah.
But what we're asked for is coordinates, which means that we need the y coordinate as well, which is what would be over here on the y-axis.
Yeah.
And the way that we get that is we put our x values into the original function. Okay? So we need to put each of them in individually.
So let's look at next is minus 5 over 3. Y is 2 lots of minus 5 over 3 cubed plus 7 over 2. This is a horrible equation.
Yeah.
For this. But
It's not that bad though.
and you've got a calculator in it.
Yeah. Yeah, because this is C2, so you've got a calculator. But even if this could be in C1. Let's try and do it without a calculator, because this could be the sort of thing you'd get in a C1 paper.
Okay.
So you've got a negative cubed is negative.
So that's minus 125 over 27.
Yeah.
Plus 7 over 2.
And then a negative squared is positive.
Plus 25
Yeah.
over 3.
Yeah.
Plus, and that's 30. Let's ignore that for a minute, let's just do 10.
Yeah. And then if we make it all over 27, shall we?
Okay. Y is equal to, so that's minus 250 over 27.
Yeah.
That one is
So we've got to times the bottom by, hang on, let's just leave it as 18. Let's see what happens.
so 7 times 25. So 4 lots of 25, so that's 175. 4 lots of 25 is 100.
Yeah.
3 lots of, yeah. And then plus 25 over 3 plus 10. That's what we've got at the moment, right?
Yeah. What about if, not very good at adding, but what if we sort of do it in bits? So what's this bit? 25.
Well, that's 30 over 3.
Yeah, so that makes
is 55 over 3.
Yeah. And then It's hard, this.
It's horrible, isn't
Yeah.
it? Should just use a calculator.
I'm just going to use a calculator. Yeah. But in C1, I think this is, we should be able to do it, to be honest.
We're just being a bit lazy.
We're being a bit lazy, yeah. So it's minus 250 over 27.
Yep.
Add 175 over 18. Add 55 over 3. Is 1015 over 54. We would probably never have got
No,
that.
not without a lot.
So what were we just finding?
Those,
That's the y coordinate.
when x is minus
Yeah,
5
so
over
that's
3. This one here.
yeah, that's that coordinate, isn't it?
Yeah. What was it? 1015 over 54.
Yeah.
So that is that coordinate.
Yeah, and then we'd need this coordinate. We don't need to bother because it's the same idea. We'd put a half in instead. So it would be a half here, a half here, a half here, work it all out, and then we'd get the other coordinate of that one. Exactly. Now, this is the thing. It says find the coordinates of the stationary points, which we have done. But with stationary points, all we did was use the fact that the gradient's 0. So dy by dx is 0. So when you've got a cubic, you've got, this is a negative cubic I've drawn, you've got a minimum point and then a maximum point, or a positive cubic, you've got a maximum point and then a minimum point.
Yeah.
Or some other complicated, like a quartic, might look something like that. And then you've got negative, positive, minimum, maximum, minimum, there might be another maximum up there. So all of these points have got a gradient of 0, and the question is, so even finding out that the gradient is 0 doesn't tell us whether it's a minimum or a maximum, it just tells us it's a turning point. And finding out whether it's a minimum or maximum, this is called classification. So you might see a question that says, find and classify the stationary points. Oh, there's the drill again. Find and classify the stationary points. So this means, is it a minimum or a maximum? And what we have is a special test, which looks like this. So the test, I'm just going to keep talking because it's going to carry on. The test function is this thing here, which is the second derivative. It's the derivative of the derivative. So what we have to do to create this test, all it does, is create a test, okay?
Yeah.
So we get the derivative, we differentiate the derivative, and then we stick our x values in, the ones that we found, and then that's going to tell us whether or not they're maximums or minimums. It's like a little magic test. Okay. This is the special magic derivative theory to test them. Okay, so if we go back to our original question and say this one, and say find and classify the stationary points, then what we're going to do now, to find them, we're going to differentiate. Then we're going to make it 0. And solve. Can't remember. Let's cheat. We did it a minute ago, didn't we? What was it?
3x plus 5 into x minus 1.
So we find out that x is minus 5 over 3, or x is a half.
Yeah.
So we know that these are stationary points, but we don't know which one's maximum, which one's minimum. So what we do is we create the test function. So the tester is the second derivative. So we differentiate the derivative again. So we get d squared y by dx squared is 12x add 7.
Yeah.
And we get that by differentiating the derivative, and then you put in, because obviously you have to put something into the test to test it. So we're going to, we're going to put in, first of all, a half.
Yeah.
And see what happens. So the test function says, six add 7? 13. Now the question is,
What's that 13 mean?
is that a minimum or a maximum? What happens when we put in x is the other one, minus 5 over 3. So the test says that the response we get from the test is
That's all right. It's minus 20 plus 7.
minus 13. Oh, 13 minus 13. I think that's just a coincidence that they're the same. But the question is, how do we interpret this answer? And what we're looking for, what the test does, is that we get our second derivative, we put our x values that we're testing into the second derivative, and they either come out as positive, we don't even care how big positive, or negative. Now, if they come out one of them, it's going to tell us we've got a maximum. If they come out the other one, it's going to tell us that we've got a minimum, right?
Yeah.
And all students would like this to be true. Minimum. Negative, minimum, makes sense, right? Positive, maximum.
Yeah. That would be nice, wouldn't it?
That would be nice,
Would be nice.
but it's not true.
No.
It's the opposite of what you think. Okay? It's the opposite of what you think. So a positive number tells you you've got a minimum, a negative number tells you you've got a maximum. So we get that second derivative, we put in our point that we're testing, so we test x is a half, we've got a positive number, so that's a minimum. And it's important to show your method to the examiner by saying bigger than naught. So here, oh, that's less than naught, that's negative, so that must be a maximum point. Make sense?
Yep.